This is question number 8. So this is an acid-base equilibrium question. They have provided us a graph of pH against the volume of sodium hydroxide added. So we started out from an acidic pH, so which is around pH 3 if you read the graph carefully, and then it goes up like this, and then it goes up, and then it goes up like that. So there is an equivalence point there, so they have labeled that as equivalence point, and there is a certain volume which is not given there. I assume it's a calculation question. There is a slightly flattened line there. There is actually the buffer region, and if you look carefully, the equivalence point is roughly at pH 8, which is just above the pH 7 for neutral pH. If I look also carefully at where this thing particular end up at, that is around pH, give or take, around pH 11, pH 12, like that. So yeah, what we could say is this is starting out from a strong, is it from a strong acid? Strong, weak acid, something like that. Let me think. I don't know why I didn't think about reading the question. The question says ethanoic acid, so we know that ethanoic acid is a weak acid, and then we have sodium hydroxide, which is a strong base. So this is a weak acid and a strong base titration. So weak acid, strong base titration. You see, sometimes when you try to do something, your brain just goes totally blank. Anyway, so in the region circle on this graph as the first part of this question, identify the two organic species that are present in the solution. As you started out with carboxylic acid, of course you know the carboxylic acid dissociates to give you the conjugate base as well as the H plus ion in solution. And of course then in the middle of the reaction, as you add in sodium hydroxide, you are doing an acid and base titration. So this is going to be a neutralization reaction. They'll give you CH3, CO2 minus, Na plus, plus H2O. What actually happened there is this is an acid-base neutralization reaction. So as this reaction goes along, this is continuously being produced in the same solution. Produced in the solution, but you still have ethanoic acid in the solution, so you still have this thing and this thing in equilibrium because you haven't reached the end point yet. So you still have the carboxylic acid as well as the you have the CH3CO2H, and you have CH3CO2 minus, Na plus. You have a weak acid and you have the salt of the weak acid. So this is essentially what you call a acidic buffer. So this is what you call an acid buffer or acidic buffer. You have a weak acid as well as the salt of the weak acid. So the two species present as required will be the CH3CO2H, which is the ethanoic acid, and you also have the salt, which is CH3CO2 minus, Na plus, as a result of a little bit of neutralization having taken place. What do they want? Explain the pH, why it only changes slowly and gradually. So the second part of this equation is basically give two equations to show why this buffer works. You know how buffer questions are usually very popular, explain or show by using two equations. What happened when you add a little bit of acid, when you add a little bit of base. This is essentially what is going on. These two are the active ingredient in the buffer. So what happened is this is the buffer region. This is the acidic buffer region, meaning the circle region. And this will resist or it will oppose changes in pH. Meaning to say, therefore, pH remains roughly constant. Roughly meaning they like to just stay the way they are. When a little bit of acid or when a little bit of alkali or base is added to it. Okay, acid or base, acid or alkali is added to it. And they give us 3 marks because we are supposed to write two equations. As you will know if you have done quite a lot of past papers, this is just a different way of asking this question. So H plus, if you add in H plus, which one in the buffer which of these will take away the H plus? The acid doesn't take away the H plus, it is the salt that will react with the H plus. So the salt is present in the reaction mixture, the buffer reaction mixture. So this is from the buffer, and they will remove the H plus added by forming CH3CO2H plus Na plus. And think about it, this is from the buffer, it removes the H plus and it forms something else which is already present in the buffer. That's why the pH remains roughly constant, because you're producing something which is already one of the two components present in this acidic buffer. On the other hand, if you have OH minus, if you add in a little bit of base or alkali, which one of these two will react and take away the OH minus? This thing is negatively charged, it's not going to react with the OH minus. In fact, it is the acid that will react with the OH minus, which is the base. So they will react with that acid, and that acid is present in the buffer, as the buffer contains two things in it. It's a two-component system. The base react with the acid to give you water, and in doing so, you will kick out CH3CO2 minus. These things are balanced in terms of atoms. These things are also balanced in terms of charges. So OH minus take away H plus, and you're left with the conjugate base CH3CO2 minus. And guess what? This is the other substance present in the buffer. As this is the other thing present in the buffer, you're not creating something new. You're just making something which is already present in your two-component system. Okay, so that's how the pH remain roughly constant, because something from the buffer will react with the H plus or the OH minus that you add in order to give you the other substance present in the buffer. So this is still question 8. Question 8A part 2. So they're giving us a lot of line, 4 lines for 1 mark. This is quite extraordinary. So they're saying that you add in the acid and the base in equal proportion, but why is this equivalence point greater than 7? I mentioned about this briefly at the start of this particular question. You can think about it in terms of what you are adding. You are adding sodium hydroxide, which is a strong base, to a carboxylic acid, which is a weak acid. So when you think about it, strong base and a weak acid, you always, when you have mixed in the equal amount, the weak base dissociate partially to H plus, so the strong base dissociates completely into the OH minus. You're gonna have the OH minus overpowering the amount of acid when we think about equilibrium here, whereas this is not an equilibrium. So that's why when you mix this weak acid and strong base, the equivalence point is just above pH 7. On the other hand, if you have a strong acid and a weak base, it's also similar argument, and your equivalence point will just be below pH 7. If you have a strong acid and a strong base, your equivalence point will be somewhere in the middle, which is much closer to pH 7. So I think we are looking at this idea, the argument of ethanoic acid is a weak acid, NaOH is a strong base, so we're looking at a weak acid and a strong base reaction. So I can just state the obvious. CH3CO2H is a weak acid. It dissociates partially into H plus ion. It dissociates partially or reversibly, or it ionizes partially into H plus ion in water. And NaOH is a strong base. It ionizes, or it dissociates, whichever word you like, completely into OH minus. As a result of it, so this is a strong base, weak acid titration. So as a result of it, your equivalence point, when you mix in this and this in equal amount, is going to give you equivalence point just above 7, because the hydroxide will overpower the amount of H plus present as a result of this equilibrium dissociation. Don't know why they give 4 lines for that thing there. Question 8, part B, is a calculation question. They have 1 whole page, is a 3-mark calculation question. What we have here is we have ammonium vanadate. Let's see what's going on. So if I have NH4VO3, this is 0.150 gram. So all of this solid dissolve in acid. What I get then is I get a solution. I get VO2 plus ions, And then I can add zinc to it. When I add zinc to it, zinc is a reducing agent. So the zinc itself will be oxidized and it will reduce the VO2 plus. It will make the VO2 plus gain electron as per the half equation shown. And then you will get V2 plus there. And you will remove the zinc by filtering any remaining zinc powder because the zinc that go into solution will be zinc 2 plus. You're going to do titration of this resulting solution. You're going to titrate vanadium 2 plus back to vanadium, what is this oxidation state here? Plus 1 is the overall oxidation state, equal to vanadium plus 2 times minus 2. So vanadium is plus 1, plus 4, vanadium is plus 5 there. This is vanadium plus 2. We're going to do titration with this vanadium plus 2 using MnO4 minus acidified. So there is manganese plus 7. The manganese plus 7 will go to manganese plus 2 in your Mn2 plus. The equation is given. On the other hand, what will happen to the vanadium 2 plus is that the vanadium 2 plus will go back to VO2 plus, which is the reverse equation based on the first line of the equation they've given you. So this is back to vanadium plus 5. So let's work backward. So this is the idea of backward titration. So I'm going to start off by talking about vanadium 2 plus 2H2O. I'm going to VO2 plus 4H plus 3 electrons. I've just reversed this equation as they have given us because we're going to oxidize the vanadium 2 plus back to the vanadium 5 plus. And I have been given this MnO4 minus plus 8H plus 5 electrons, giving you Mn2 plus 4H2O. We need a balance equation to do stoichiometric calculation. You can hopefully see 3 electrons and 5 electrons there. You need a lowest common multiple called LCM, primary school mathematics. 3 and 5, you're gonna get LCM of 3 times 5, which is 15. So I need to multiply this equation by 5. I need to multiply this equation by 3, and then I add them up together. The question is, do I want to add them up together? Okay, maybe I add them up together first. I will have 5 times 2, which is 10H2O on the left. I will have 4 times 3, which is 12H2O on the right. So 10H2O on the left, 12H2O on the right will give me a net balance of 12 minus 10, which is 2H2O on the right hand side. So I'll get 2H2O on the right hand side. I will get 5VO2 plus on the right hand side as well. I will get 3 Mn2 plus on the right hand side as well. How about the H plus? The H plus, I would have 20H plus because 5 times 4 is 20H plus on the right. I'll get 15H plus on the, 24H plus on the left, 24H plus, 20H plus, so give me 4H plus on the left hand side. So 4H plus. And what else do I have? My electrons will cancel out and I'll get 3 MnO4 minus. And I think that equation should be balanced out very nicely. 5 vanadium, 12 oxygen, because 3 times 4 is 12 oxygen. 5 times 2 is 10, 10 plus 2 is 12 oxygen. Okay, 3 manganese, 4 hydrogen, internal charges, plus 2 times 5 is plus 10, plus 4, so it's plus 14. This is minus 3, plus 14 minus 3 is plus 8, is it? Plus 10 plus 4 is plus 14 minus 3 plus 11, okay, this is plus 5 and this is plus 2 times 3 is plus 6, plus 6 plus 5, well, plus 6 plus 5 give me plus 11. This equation is balanced because we started from something which was balanced and all we did was we did the correct multiple based on lowest common multiple. Anyway, so what do we know? We know that this is impure, okay, this is impure. What is the pure stuff? The pure stuff is the VO3 minus, since this is NH4 plus. How much VO3 minus is in here? But this VO3 minus in H plus is going to be the same as VO2 plus. Therefore, the mole of the VO3 minus, or rather the mole of the NH4 plus, is equal to the mole of the VO2 plus, because I am just adding acid. So the mole is the same. Okay, And you could imagine that because this is VO3 minus is also vanadium plus 5. Since it's minus 1 equal to vanadium plus 3 times minus 2, the vanadium is plus 5 in there. It's just in acid, it changes to a different form, but it's still vanadium plus 5. What else can I say? What else can I say? Let's do the titration calculation now. Step 1. So I have the amount of these, and I want to know the mole of the vanadium 2 plus. Okay. Do I want to know the mole of the vanadium 2 plus? Let's see. Nope, not really, because the vanadium 2 plus come from the vanadium, well, this is vanadium 5 plus to begin with. So it is this one that reacts with zinc to reduce it back to this. So however this much is, will give you that. So we're looking at the mole of the VO2 plus instead of the vanadium 2 plus. This is our reactant, but this was obtained by reducing this with zinc. So the mole of the VO2 plus is to the mole of the manganate 7. 5 is to 3. This is how I set up my mole balance ratio from the balance equation. Okay, so label, and then from the balance equation, and then what is the actual amount? This is the actual amount of the mole, and then at the bottom is going to be my value. So convert cm cubed to dm cubed by multiplying by 10 to the minus 3. That means divide by 1000, and then mole equal to concentration times volume. This is mole, this is mole. Everything is to do with mole. The top bit is reserved for this based on what I label. If you have got the label the other way around, doesn't matter. This would be the other way around, this would be the other way around. So the mole of the VO2 plus, actual mole, bring that up. So there's going to be 5 over 3 multiplied by 20.10 times 10 to the minus 3 times 0.0250. And I got my calculator at 0.375 times 10 to the power minus 4 mole. This much mole, this will give you that in your reduction. So the amount of these is equal to the amount of these present here. So what we have is the amount of this here is the same as the amount of the ammonium vanadate 5 there. So the amount here is the same as the amount here, which is the same as the amount of this, the reactor with the MnO4 minus. So what I can say is the mole of the ammonium vanadate is going to be the same as the mole of the VO2 plus that I obtained when I dissolve this in excess acid. I want to know the mass of this. So on the left hand side, I'll have mass over the MR, which means I need the MR of ammonium vanadate. So straight onto the, it is given 116.9. So 116.9, that will give me mass over MR, which is the mole of that solid, is equal to this much mole from the reaction. So there's 8.375 times 10 to the power minus 4 mole. Bring that up. So that was our previous answer, multiplied by 116.9. That gave me a very long list here, but I will just round it up. So 0.097904, because the next number is 375, so I will just round it up there. This is not my final answer. This means out of the 0.150 gram, which was impure, only this much is the percentage of NH4VO3. So it's 0.097904 gram divided by your original mass, which was the impure sample, times 100%. So what you have now is gram and gram cancel out. So that previous answer divided by 0.150 times 100, I get 65.269. They want the final answer to 3 significant figure. So I look at the next number. Oops, sorry. Don't know why that. Hang on. Yep, okay. So this is the number next to the 3 significant figure. So this is more than 5. So I need to add 1 there, which gives me 65.3%. And this is to 3 significant figure there.